Thank you everyone for joining. I am Francesc Estrogues, Applications Engineer at MPS, based in Barcelona. And today I'm presenting the webinar on designing a power tree for automotive SoCs. So the agenda for today is a brief introduction on the topic for those who are not familiar. And then we will dive right in. First, understanding the system-on-chip power requirements. When it's the first time you are presented with the system-on-chip power requirements, maybe it's not so easy to understand them. So we'll do a quick guide. And after that, we will also present what are the challenges for automotive batteries. So usually these kind of processors are traditionally found in computers, server racks, and they are powered from a clean or a relatively clean 12-volt bus or 48-volt bus. In the automotive environment, this is not the case. The car battery, it is nominal 12 volts voltage, but it is very noisy. There are loads turning on and off, so it is more challenging. After that, we will be able to select the right pre-regulator architecture for our needs, and we will select the pre-regulator bus voltage. It's usually between either 3.3 volts or 5 volts. We will see what are the benefits of each. With all the requirements, we will select the optimal IC for this pre-regulator power stage, and we will check if we need to add any other system protections to operate with a car battery. So as an introduction, lately in ADAS, which are driver assistance systems in the car, and infotainment system on chips are offering increasingly higher computing power to enable high-level autonomous driving and optimized user experience. This has led to an increase in power consumption from these SoCs, more demanding power converter performance. You need to keep a very tight regulation, don't allow any overshoot or undershoot take place during the load transients, and overall have a very good DC performance. And last, it has increased the power density. Here on the right, you can see an example of an SoC platform for an autonomous car. And you can see how this kind of PCBs need to have a very high level of functional safety. So they have systems that are redundant. So one PCB is packed full of components, as you can see here. This makes the thermal performance of our power converters very important. We don't only need to dissipate heat from the SoC itself, which are very power hungry, but we also need to take care about the power delivery efficiency and thermal performance. So understanding the SoC power requirements, usually when when reading the datasheet for an SoC, we are presented with a table similar to this one, or in a different form. But basically what it mentions, it's the different rails that the SoC needs. Here on the left column, we got, for example, VDD core, 1.8 volts, GPIO, and so on. These are just generic names. And each rail has assigned voltage, current, transient load, slew rate of this load, and the tolerance that it requires. This is easier to understand graphically. So let's do this. On the top graph, we can see the rail voltage in green. Okay, here in this case it's 0.85 volts, and then in red we got a load, a current profile for this rail. So let's try to assign each requirement on the power this graph. First, we got the rail voltage. This is self-explanatory. It's the DC level or the nominal level of that this rail requires, in this case at 0.85 volts. Then we got the maximum current. Usually in the table, the peak current is specified. The typical or the average current in the rail is usually lower, but we need to design it so that it can supply the maximum current needed. In this case, for this rail, it's 60 amps, as you can see here on the peak. Then we got the transient load magnitude. This can be represented as an absolute number. In this case would be 40. So we got a change from 20 amps to 60 amps. That's a 40 amp transient load magnitude, or it can be a percentage. They can say it's 60% of 60 amps of the maximum current. So we would change from 40% to something like that. Then we got the slew rate. This change in load current happens over time. It's not instant, but this time can be quite short. This is presented usually in amperes divided by microsecond, and it is basically the ramp of this load change. And at the end, we got the voltage tolerance. So when the current is changing, our controller will try to keep regulation on our output voltage, but it always has some undershoot and overshoot. We need to keep those within the voltage tolerance, but not only that, we also need to account for the converter accuracy. So if here, for example, we got a +3 and -3% window, in this window, we need to account for the converter accuracy, which may be 1%, 1.5%, depending on the specifications. The overshoot and undershoot during a load transient, even line transient, and so on. So it's quite demanding for our converters. The next challenge we find is the supply. So not only it is hard to power a load like an SoC, but it is hard to power it in the automotive applications. So the car battery here on the bottom is nominal 12 volts, but it is powered from an alternator, and it has all kinds of loads connected to it with very long harnesses. So it is a very noisy environment. We can see here on this graph, this comes from a previous webinar that MPS hosted on this topic. If you are interested, it is published on our website. But to keep it simple, there are several conditions that we need to take into account. First is the crank condition. This is when the starting engine turns on. Depends on the weather, if it's very cold or if it's warm. This can take more power from the battery and make the battery voltage drop to a low level during a certain period of time. If the weather is quite warm, this can be maybe 6 volts or 7 volts compared to the nominal 12 volts. But in a very cold environment, this can drop as low to 3 volts. So we need to make sure that our converters can operate in those conditions. Then we can also see alternator noise. This is on top of the nominal 12 volts. Some AC voltage can be coupled into that. So we need to avoid, we would need to rectify this voltage to avoid having negative currents on our devices. Negative currents on a power converter, depending on the magnitude, can damage the device. The next challenging transient that we can find is load dump. This is when some of the loads on the high power loads on the system, in the automotive system, are turned off. Suddenly there is a lot of energy in the cables that need to be dissipated somewhere. This can make the voltage at the harness rise up to about 100 volts, but this is usually suppressed by the car to about 40 volts. So our converters that are connected to the car battery need to survive at least 40 volts. And then there are some other conditions that can happen during service, like jump start or a reverse battery connection. Okay, so here we got the first draft of our power tree. This is very simple. We have taken the different rails on the table and draw them into a box here on the right. This is a generic SoC with all the different rails it needs. And also DDR could be 5 or 4. Usually needs a couple of or 3 voltages to supply it. So we have assigned to each a DC-DC converter, since each needs to be powered from a different source in this case. We have also assumed that they are all switching converters. So we added an inductor. We have assumed this because the currents are not low. The lowest current that we got here on this requirement is 1.5 amps, and that would be a bit too much to power from a linear converter. The heat dissipation would be quite high. So we just assume that there will be some inductors we assign the voltage for each. And we name them DC-DC 0 to DC-DC 7, just for simplicity. We also know that there is a rail that requires 60 amps. This is usually not powered from a regular buck converter, like the ones that we are familiar. This is sometimes powered by a controller IC with some discrete DR MOS, which means a driver MOS. Those include the gate drivers and the half-bridge FETs. This is a very common topology in computing. The other converters, since they are quite a lower current, they can be powered with regular buck converters. Typically, all these devices, the DR MOS and the buck converters for low voltage and high current, have a very low input voltage range. Usually they can tolerate about a maximum of 5.5 volts. During certain time, maybe 6 volts, but we should keep the voltage below 5.5 volts on this input. And we need to have a voltage higher than 3.3 volts or equal, since some of the rails require to output 3.3 volts. So here we got, well, not a problem, but a situation where we got a car battery that can go up to 40 volts. It can have reverse polarity. It can have a worm crank, so it can drop the voltage to about 6, 5, or 3 volts, depending on the conditions. We need to interface the car battery with low voltage DC-DC converters, and this is where the pre-regulator comes in. So the first step to decide which pre-regulator we are going to use is to decide on the topology based on the specifications. We have presented here 3 different cases. Maybe there are more, but that would be going very in depth. So the first case would be if our system must operate during a worm crank event. During a worm crank, we can consider that the input voltage on our pre-regulator will drop to about 6 volts, 6 or 5 volts. If all our system only requires voltages below 5 volts, we will be fine. We can supply this lower voltage even if our input drops. So we could use a buck converter, so a step-down converter. If we must operate during a worm crank event, but some circuits require a voltage exceeding 5 volts, for example, some camera sensors, some antennas, this kind of ADAS sensors sometimes are usually are powered from a bus at about 8 volts or 10 volts. Then we would need a downstream boost converter. We first generate a 5 volts bus or a 3.3 volts bus, and then we have later on we have a step-up converter to bring up again the 8 volts or 10 volts for these sensors. Since they are quite low power, this is usually the most cost-effective way to power them. And if our system must operate during a cold crank event, remember that this can bring the voltage down to about 3 volts, then we might need to consider a buck boost converter, but this is not very typical. So for simplicity, in this example, we have set the requirement to operate during worm crank. We don't have any voltage rail that requires a voltage above 5 volts, so we can just select a buck converter. Now we know we have a buck converter from the car battery to our low voltage domain, but we need to select which voltage we are going to supply to this bus. We also know that one of the rails will need to be powered by a converter plus DR MOS. If we look at the voltage specification for those, they require a voltage between 4.5 volts to 5.5 volts as a supply. So we know that at least we will have to have a 5 volts supply somewhere in our system. Then we can take a look at the other converters, their output voltages and currents. We can see that the highest voltage that we need to supply to our SoC is 3.3 volts at 5 amps. So we could power all these voltage regulators from either a 5 volts bus or a 3.3 volts bus. So we should try to find what is most cost effective or what is more suited to our system. To check if it makes sense to use a dedicated 3.3 volts bus, for the lower current rails, we can calculate the power that they need. They would be, we call that regulator 2. So this is regulator 1 would be the high current rail, the 0.8 volts, 60 amps. And regulator 2 are all the other rails that together don't have so much power. To calculate the power that they need, we can just add we can sum the product of their voltage by their current of each individual rail and divide that by the efficiency. We could be very accurate and try to estimate the efficiency for each individual rail, but for simplicity in this demonstration, we are just assuming regular efficiency, general efficiency of 89%. So we are dividing all these products by 0.89. Some rails will have higher efficiency, some rails will have lower efficiency, but based on our experience, since we deal with power converters all day, we know that 89% is quite a good number to calculate this. So we add all these powers, and we get with a total power of 45.5 watts for these low current bus rails. Now we need to calculate what load current we would need to deliver these 45 watts. We do that dividing the total power by the voltage. If we were using a 3.3 volts bus, we would require to deliver 13.8 amps of output current. On the opposite side, if we were using a 5 volts bus, we do the same operation, we would only need to deliver 9.1 amps of output current. So the output current of the 3.3 volts bus exceeds the output current of the 5 volts bus by about 50%. So from our experience, dealing with lower currents is usually more efficient. It is easier to do the layout. It is easier to ensure good power integrity. So in this case, using a 5 volts bus is preferred for us. If you remember, we need 5 volts bus to power the high current rail, the controller plus driver bus. And now we have decided we also need a 5 volts bus to power all the low current domain. So should we consolidate those into a single converter? First, we can calculate the power that we need for the high current rail. This is also, again, quite simple. We multiply the voltage by the peak current, divide by the peak efficiency, and we get an output power on the high current rail of 57.3 watts. For the low current domain, we already calculated that at 45.5 watts. So if we add those, we get the total power for our SoC system of 102.8 watts. If we do the math, our pre-regulator will need to deliver 20.6 amps at 5 volts. Here is the topology that we are proposing. The battery voltage is supplied to the pre-regulator, only one stage, which delivers 5 volts and 20.6 amps. Another option would be to separate the high current domain and the low current domain. So instead of having a single converter, we have 2 converters delivering each 5 volts, but one is delivering 11.5 amps and the other one is delivering 9 amps. From our experience at MPS, we have seen that it is usually easier to handle 2 low current buses than a single 20 amps bus. So a power converter that can deliver 20 amps is not easy to implement in automotive ECUs. There's a lot of power dissipation concentrated on a single spot. Also, the layout tends to be, the area they take tends to be quite high. The inductor is big, the FETs are big. So this tends to radiate a lot of EMI, electromagnetic interference. It is usually easier to contain the EMI of 2 smaller regulators and to spread the heat into 2 different regulators than have everything on a single DC-DC converter. So in our case, we select to have 2 different pre-regulator stages to both spread the heat and contain the EMI. So now we got all the requirements for this pre-regulator device. We know that it needs to tolerate a load dump up to 40 volts. It needs to be able to operate in warm crank down to about 6 volts input. And it needs to deliver an output current above 11.5 amps, since that is the peak that we will need during operation. We can go, for example, to MPS website and filter on the automotive product section. You have the link below. We can filter our converters by input voltage, output current, and some other parameters. So we'll start to check there. First, we filter by the input voltage. We know that our converter must operate up to 40 volts input. So to have some margin, we filter by converters that can tolerate 40 volts up to 50 volts. We don't want converters that can tolerate higher voltages because that is not needed. And we would be paying overhead for those bulky MOSFETs that can work at high voltage. So we want to really narrow down our search to devices that can operate between 40 and 50 volts, since that will be the most cost-effective solution. Then we know that our input voltage can drop to as low as 6 volts, so we need converters that can operate from 6 volts to lower voltage. In this case, 2.2 is the minimum that the filter allows us. It's okay if it's lower than 6 volts. And we know that we need an output current capability of above 11.5 amps. If we filter here, the higher that it allows us is 11.99 amps, but no results appear. So maybe what we can do is lower the current that we can use and enable the next step, which is a multi-phase capability. If we don't have any converter that can deliver 12 amps by itself, maybe we can parallel 2 of them. Now, with all these filters selected, the MPQ4360 appears. This is a 40 volt tolerant device. So first requirements checked. It can operate to a minimum input voltage of 3.3 volts. So the second requirement is checked. And each converter can deliver 6 amps, and it has multi-phase capability. So we can parallel 2 of them to achieve the total 11.5 amps. In this case, we could even achieve 12 amps. So a brief introduction on this part. This is a buck converter that can operate from 3.3 volts to 45 volts input range. So it is perfect for our application. Can deliver 6 amps with multi-phase capability, so we can parallel as many of them as we need for the application. And it has a low IQ of about 10 microamps. This is perfect when being powered from the car battery. And it has other features that are very useful for the application. One of the most useful features is the sync input and sync output clock that it has. So in this topology, when paralleling them, we can set one device to be the master and another device to be the slave. The master device will provide a clock from the sync out pin to the slave, which is connected to the sync input pin. This clock is a 180 degrees phase shift, so both converters will be operating in an interleaved operation. This is quite good to improve EMI and to reduce the output ripple. Then this part also has an ICS pin, which is used to share the current information, so we can make sure that both phases are delivering the same amount of current. We can connect those pins together, so they will be delivering both half the total output current. To finish, let's check if we need any other system protections. So the MPQ4360 Pre-Regulator can protect the systems against low damp voltage, since it can survive 40 volts. But it can still be damaged when the battery polarity is reversed. We need to add something to protect the pre-regulator from the nasty conditions at the car battery. The typical protection would be placing a diode in series with the input line. Here we got a schematic of a typical evolution board. We got on the left the car battery input, VBAT, we can have a TPS or not. That is not 100% required. Then we got some filter capacitors, and we got a diode, D1. After the diode, we call that usually VVAT protected. This diode has an issue. It has a fixed forward voltage that when the current is conducting through it, we can multiply the current by its forward voltage. We will get the power dissipation at this diode. In this SoC system, when the input voltage drops during the warm crank event, we can have input currents that exceed 8 amps. This would cause a very high dissipation at the diode. Even on a Schottky diode that has a quite low forward voltage, at 8 amps, this would cause a dissipation of about 2.5 watts. That is too much. Here on the lower right corner, you can see a picture. This is not the SoC system. This is just a regular evaluation board delivering about 15 watts to an output, and the input is protected by a diode. You can see how even for this low power system, the diode is hotter than the DC-DC converter itself. If the input current were higher, this would get out of control very easily. So another option that is much more efficient would be to use a P-channel MOSFET circuit that disconnects the input when the voltage is reversed. This addresses the negative DC polarity, but these kind of circuits are too slow to rectify any superposed AC voltage on the input line. All the automotive ECUs need to pass a certain amount of tests, and one of these tests is to superpose an AC voltage on the input line. This AC voltage can sweep from a low frequency to about a few hertz up to about 100 kilohertz. At about 5 kilohertz or so, this P-channel FET circuit is too slow to turn on and off, so it can no longer rectify the negative currents, and it can risk damaging our ECUs. To protect these high power circuits at MPS, we propose using the MPQ5850, which is an ideal diode controller that uses an N-channel MOSFET, not a P-channel, and it emulates a diode. Here on the right, you can see the simplified schematic. We got the input voltage from the car, and on the right, we got the output voltage to our system. In between, we got the FET M1, which has a body diode in the same direction as we would place the diode to protect our system. What this controller does is that during forward conduction, the FET is fully turned on. So instead of having a voltage drop on our diode, we just have a very low resistance path on the FET. This could be a couple of milliohms up to 10 milliohms, depending on the FET that we choose. But this is much, much more efficient than just having a diode there. In the event of negative currents, the controller will quickly turn the FET off to block the reverse current and protect the circuitry. Here we have a graph. Let me guide you through this. So on yellow, we got the input voltage in, which has a DC level of 12 volts, but it has superposed to it an AC sinusoidal voltage. On red, we got the output voltage after our protection device. You can see how it is being rectified compared to the input voltage. When the input voltage is higher than the output voltage, the part will fully turn on the FET and allow conduction. And as soon as the input voltage drops below the output voltage, the part will quickly turn off the FET and block the reverse currents. Here you can see in blue the current, the input current. When the part is turned off, when the FET is turned off, the input current is 0. As soon as the input voltage exceeds the output voltage, the FET is turned on and some current is allowed through it. And then once the current crosses the 0 and becomes negative, the part will very quickly shut down the FET and avoid the negative currents. This part integrates a boost converter to generate the gate to source voltage for this M1 FET instead of a charge pump. Charge pump circuit can be more cost effective, but it doesn't have a very high drive capability, so it cannot turn off the FET quick enough. This boost converter is very low power. It is very compact. It uses a maybe 2x2 millimeter inductor because it doesn't need much current. It just needs current when turning on and turning off the FET. So with everything selected, protection and pre-regulator, we can now draw our first power tree of the pre-regulator. We got on the left the car battery. The car battery is protected by the MPQ5850 from reverse battery conditions and reverse currents. And then we got two different pre-regulator buses. The first one is powered by two MPQ4360 working in multiphase, delivering 5 volts and 11.5 amps to the core DC-DC converter, the high current one. And then we got another pre-regulator bus on the lower end, again powered by two MPQ4360s, since the current level is quite similar. And this one is delivering 5 volts and 9 amps to the low current DC-DC converter. We have seen that there are three main topics to consider when designing the pre-regulator for an SoC. First is to select an IC that can operate correctly under all the automotive battery conditions. So load damp, warm crank, deliver enough power, tolerate the ambient temperature, and so on. We have also seen that typically a 5 volts bus is more cost effective than a 3.3 volts bus. It can be inadequate in certain applications. For example, if one of our low voltage buck converters were not to tolerate 5 volts, then we would need a lower voltage, but it is usually more cost effective. It is both more efficient to generate a 5 volts from 12 volts input compared to 3.3 volts. And it is also usually more efficient for the low current regulators to be powered from a 5 volts bus than a lower voltage. And we have also seen that when the input current is quite high, which is the case for these powerful ADAS systems, an ideal diode controller is the most efficient way to protect the system compared to a diode or to a P-channel MOSFET. So that's all for me. If you have any questions, we are happy to answer now.
Thanks, Francesc. Great presentation. I want to remind everyone that you can mouse over the bottom of the Zoom webinar interface and you will see the Q&A button. Please type in any questions that you might have. As we are waiting for more questions to come in, I want to remind you that we are recording this session and it will be available later on demand. We will send you a link early next week. With this link, you can watch today's webinar on demand, and we will also send you a link to the presentation itself. Please also check our MPS webpage, and you will find a webinar schedule to see additional sessions. So let's get started with the first question. When would it make more sense to use a 3.3 volt bus instead of a 5 volt bus?
Thank you, Julian. So it would make more sense to use a 3.3 volts bus if one of our regulators required a lower voltage than 5 volts. Some PMICs required to be powered from 3.3 volts instead of 5 volts, depending on their voltage tolerance. Also, if our system would need to survive or to operate during cold crank, since the input voltage can drop below 5 volts down to about 3 volts, it may have a lower effect on our output if we're outputting 3 volts instead of 5 volts. The input voltage would be closer to our output. And if we had a 5 volts output, this would be higher than our input voltage. Our step-down converter would not be able to supply that very well.
Okay, thank you very much, Francesc. Let's continue with the next question. Regarding P-channel for reverse protection, what about its body diode as rectifier?
So in the typical P-channel FET, I'm not sure if everyone is familiar with that, but this is a very typical solution used in many consumer applications. Just a P-channel FET that its gate voltage is limited by a zener from the input, the diode is placed, the FET is placed in a way where the diode is it has the anode on the input and the cathode on the output, so it is also rectifying the output. It will not allow conduction during reverse battery protection, so it should not be an issue.
Thank you very much, Francesc. Next question is, if my system current consumption is 2 amp at 12 volts, can I use diode instead of PMOS?
Yeah, 2 amps. So let's suppose we are using a Schottky diode. This could have forward voltage of about 0.3, 0.4 volts, depending on the device used. This device, this forward voltage of 0.3 volts, if you multiply that by 2 amps, this would cause a power dissipation of about 0.6 watts on your diode. So you would need to design the PCB layout to be able to dissipate this heat from the diode. I think 2 amps could still use a diode, but it will get quite hot. Depending on the ambient temperature that your system needs to operate, you might need to consider a FET instead of the diode.
Next question would be, can we use heatsink for the SoC in case of overvoltage?
I'm not sure I understand the question. Overvoltage.
It was perhaps the person who has asked this question can rephrase it, but I will repeat it to you, Francesc. It was, can we use heatsink for the SoC in case of overvoltage?
Yeah, I don't see, so the SoC has a heatsink to dissipate its power loss, but I don't see how that would help in the event of overvoltage.
Okay, let's continue. Next question is, does MPS have automotive PMICs with integrated LDOs, that PSRR and output noise density included in the datasheet? All your automotive PMICs datasheet missing information about PSRR and noise density of the integrated LDOs.
Yeah, I cannot answer for all the datasheets, but I think, so I'm not sure if they are included in the datasheet. In case they are not included in the datasheet, we can for sure provide this information to anyone that asks and requires this information. But if it's not in the datasheet and you need that, please accept my apologies. We'll try to add those to the newer devices. But anyway, you can just ask your local FAE, and we should be able to provide this kind of information. We for sure do these measurements, and we have done them before.
Okay, thank you, Francesc. Next question would be, what are the drawbacks of paralleling 2 buck converters like you proposed for this solution?
So the main drawback would be that for each phase in the buck converter, you need 1 inductor, and you need a certain amount of passive components around it. They are usually quite cheap, so the inductor is the main cost driver. Instead of using 1 large inductor to deliver, for example, 12 amps, you are using 2 smaller inductors to deliver 6 amps. The total cost depends on the inductor that you are going to use, but it could potentially be a bit more expensive than having a single stage. But in our case, we think that the benefits that the smaller layout gives for EMI and the distributed thermals give on the total thermal performance of the PCB can outweigh the cost differential of paying for an extra inductor.
Okay, thank you very much, Francesc. Do we have any other question here? We will pause here now for a little bit and give you the chance to type them in. Feel free to ask anything that you had a question on, as we would love to have an engaged and fruitful discussion. So we give you a few more time to type in questions if you might have any. So there's one more question. It is a P-channel MOSFET works just fine for reverse polarity protection. Why would the MPQ5850 be needed?
Yeah, as I mentioned, this is for automotive applications. So to qualify an automotive ECU, we need to pass a series of tests. For the 12 volts battery, they are called LV124. There's also some ISO on that. And one of these tests is one of the required tests is that the ECU needs to be able to survive and operate normally when there is an AC voltage superposed to the nominal 12 volts. So not only when the car battery is connected reversed, that would be fine with a PFET, but when the car battery is connected in the correct polarity, but there is an AC voltage on top of it. This AC voltage, if it's not rectified, it can charge and discharge our capacitors and even get some negative current through our power devices and any other semiconductors that are connected to the power line. To avoid this, we need some circuit that is quite fast, and it can rectify this AC voltage. Their frequency can be from very low hertz to hundreds of kilohertz. Each year, the standard gets more demanding with a higher frequency. So to do that, we need something that is switching fast. It is able to turn on fast and turn off fast. In this case, the ADL diode controller is ideal for this case. The PFET, the circuit that it uses, the gate is polarized through resistors. There are some capacitors to make it stable. This is an RC filter, which makes it very slow.
Thanks a lot, Francesc. So I do not see any other questions coming in. So thanks a lot to all of you for joining. And as I mentioned before, we will send a link to the presentation via email, and the session will be available on demand. For those of you who joined a little bit later, we will have the same session tonight at 5 p.m. CET. And yeah, we want to thank everyone for joining and remind you to look out for future webinars that we are producing. Hopefully, we will see you back again here soon in the near future. And thanks again. Have a nice day. Bye.
Hey, Julian, there is another question. So
one more. Sorry. Yeah. Let's have the last question here. Are there any buck boost converter power supply solutions available from MPS, also for the 20-volt low voltage side battery, e.g. truck applications?
Yeah, I believe our buck boost converters, automotive grade, are only, I think we only have buck boost converters that can operate up to 40 volts. So that would be for a 12 volts battery, not for truck. But I would like to know which application requires a buck boost when powered from a truck. Sorry, since usually the 24 volts battery, even during cold crank, doesn't drop to a low voltage, such as the 12 volts battery. We could analyze that requirement.
Okay, thanks a lot. So yeah, thank you very much for everyone again for joining this webinar. And as I mentioned before, we will send the recording of the webinar, and we are looking forward to seeing you soon in one of our other webinars. Have a nice day and see you soon. Bye.
Thank you, Julian. Bye-bye.
Bye.